Hi, this lecture is going to be about discrete time Markov chains. It'll be a quick recap since I'm assuming you're all familiar with this material already. So let's start. Let's start with with defining what a stochastic process or random process is. So a random process is a collection of random variables xt indexed by time, which we denote by little t. Capital T denotes the set of all possible times, so it's the index set. The random variables themselves take values in some other set S, which we'll call the state space of the process. And this is some abstract set, but it will be discrete, meaning that it's either finite or countable throughout this course. So depending on the index set capital T, we call this a discrete time process if the index set itself is discrete. So the time could take values either in the natural numbers or the integers, or maybe in a finite set. These are all examples of discrete sets. We call it a continuous time process if the index set is continuous, and examples of this are the real line, the positive reals, or an interval such as 0 to 1. Okay, and here's a concrete example. So toss a coin repeatedly and note down all the outcomes. Then we get a sequence of heads and tails, which are all independent of each other. And this sequence is an example of a random process. This is not a very interesting example. So next, let's move on to a slightly more complicated example. This is going to be a drunkard's walk. So we have a street. The drunkard lives at one end of it, and there's a pub at the other end of it. And there are a number of lampposts down the street. So the drunkard starts at the pub and sets off home. When he comes to the first lamppost, which is lamppost number n, he pauses for a while, rests against it to regain his balance, and then resumes his walk. Unfortunately, while he's been standing here, he's forgotten which direction he's walking in, so he's equally likely to head back to the pub or head towards his house. Okay, let's say he heads towards his house, reaches lamppost n-1, then he repeats the process. He pauses there for a bit and resumes walking, equally likely to walk towards his home or towards the pub. And this continues until he reaches either his home or the pub, at which point he stops there. So if we note down the position of the random walker, the successive time he stops, so the first time he's at lamppost n, then at n-1, then maybe back at n or at n-2, and so on until he reaches home or the pub. Then at these discrete time points, his position takes a value somewhere in the set of lampposts or the home or the pub. And the sequence gives us an example of a random process. And the claim is that this is an example of a Markov process. Let's say a bit more about this process to see why it's Markov. Firstly, the state space of this process is the lampposts 1 to n, and the home, which we'll denote by 0, and the pub, which we'll denote by n+1. So these are all the possible states. We denote by xt the position of the drunkard at time t, and if at time t he's at lamppost number k, then there are only two possibilities for where he can be at time t+1. he either walks right and is at lamppost k plus 1, or he walks left and is at lamppost k minus 1. And given the verbal description of this process, both these events have probability half each. Okay, and the thing to note is that these probabilities do not depend on what happened in the past. The drunkard has no memory of how he got to where he was. He doesn't remember whether he came from the left or from the right. So where he was at previous times don't influence which way he's going to walk in future. Now, okay, a bit more formally, the conditional probability that at time t plus 1, he's at position y, given that he was at x at time t, and everything about the past is the same as the conditional probability he's at y, given that he was at x at the last time point. And this property is called the Markov property. So this independence of the past is what's called the Markov property. And any stochastic process with this property is called a Markov process. Okay, and we can think of other examples. So a very simplified model of weather in which today's weather only depends on yesterday's weather is a Markov process. And you'll see an example of that kind in your first homework sheet. Another example, which is not quite Markov, which we are all familiar with from our phones, is predictive text. You could think of a very simplified model of predictive text, which only predicts the next letter that you're about to type based on the current letter, and that would be Markovian. What our phones actually use is more sophisticated. They look at dictionaries to see what word you might be typing, etc. So they are not quite Markovian, but a simplified version of predictive text could be a Markov process. Okay, so those are some examples of Markov chains, discrete time Markov chains. So how do we describe a Markov chain? We can characterize it by specifying all the one-step conditional probabilities. So in the case of the drunkard's walk, we specified that from any state k, there are two possible transitions to k plus 1 and k minus 1, and we gave their probabilities. And by doing so, we specified the dynamics of this process. More generally, for a Markov chain on any state space S, we have to specify all the conditional probabilities given that it's in state x at time t. What's the probability it ends up in state y at time t plus 1? In most of the examples we look at, the Markov chain will have one more property. This is not needed for it to be Markov, but it will have the property that these conditional probabilities don't depend on the time. So the probability of going from state x at time 10 to state y at time 11 is the same as going from x at time 35 to y at time 36. The dynamics stay the same over time. The conditional probabilities stay the same over time. And if the Markov chain has this property, we call it time homogeneous. Okay, so if the Markov chain is time homogeneous, then we can represent all these conditional probabilities in the form of a matrix, an S by S matrix, which we'll denote capital P, its elements by little p. So little p sub xy is the probability of going from x to y in one time step. And if we specify these for all states in the state space, I claim that we have specified everything we need to about the dynamics of this Markov chain. Okay, okay, so the Markov chains we see in this course will all typically be time homogeneous. It's not more complicated to drop this assumption. It just needs more notation. You need one such matrix for every time. Whereas if it's time homogeneous, one matrix specifies the evolution for all time. Okay, property of the matrix P. Its elements are probabilities, so they have to be non-negative. And if you look at the row sum, so if you sum over y, pxy, then what you are doing is fixing x, you are summing over the probability of going to any state y. So you're considering all possibilities, and the probabilities have to add up to 1. So all the rows have to add up to 1. And any matrix with these two properties, namely non-negative elements and row sums equal to 1, is called a stochastic matrix. Okay, and the final observation is that in writing P as a matrix, we have implicitly assumed that the state space is discrete, and that's the only kind of state space we'll deal with in this course. If it weren't discrete, then you would have an operator rather than a matrix, and the techniques are quite different. Good. So what have we done so far? We have defined what the Markov property is, what makes a random process a Markov process, and how do we describe a time homogeneous Markov process. Now, okay, so I claim that the matrix P together with the initial condition tells us everything we want to know about the Markov chain. And what do I mean by everything we want to know? What I mean is that knowing these two things, you can work out all possible joint distributions. Let's start with the simplest example, two-step transition probabilities. So let's say we start in state X at time 0. We want to know what the probability is we end up in state Z at time 2 time steps later. How do we work this out? We work it out by conditioning on what happens at time 1. So starting in state X, at time 0, we end up in some state Y at time 1, and then move on to state Z at time 2. And we have to sum up over all possible states Y in which we might end up at time 1. This is just the law of total probability. Okay, so that gives us the first equality. The second one, so here we have the intersection of two events. X2 is Z and X1 is Y. So the joint probability of these two events is the probability of one of them, say the probability X1 is Y, times the conditional probability X2 is Z, given X1 is Y. Okay, and everything is conditioned on X0 equals X as well, so we carry through that conditioning. So the first line was the total probability formula. The second line is the conditional probability formula. And now we use the Markov property. So what's the probability X2 is Z, conditional on X1 is Y, and X0 is X? Since X is a Markov process, what happened at time 0 is irrelevant if we know what happened at time 1. So this conditional probability is the same as this conditional probability. We can drop the conditioning on X0 equals X here. So we just get the sum over Y, the conditional probability of X1 is Y given X0 is X, times X2 is Z given X1 is Y. Okay, and in terms of our transition probability matrix, the first term here is Pxy, going from X to Y in one time step. The second term is Pyz for going from Y to Z in one time step. And we are summing over all Y in S. Okay, what's this sum? You recognize this as just the formula for matrix multiplication. So this is the xz term of the product of the matrix P and the matrix P. So it's the xz term of P squared. In other words, the two-step transition probability is just P squared. By the same reasoning, the three-step transition probability matrix is P cubed. The 27-step transition probability matrix is P to the 27, and so on. Now, what if we want to calculate joint distributions, which I claimed we could do? So what if we want to know what's the probability that we are in state X at time 3, in state Y at time 17, and state Z at time 23? Well, we need, okay, there's no way of calculating this first term. It has to be given to us. So the probability that X3 is X. But if we start in X at time 3, then to get to Y in state 17, meaning in 14 time steps, the conditional probability is P to the 14, XY term. And then in another 6 time steps, we want to go from Y to Z, and the probability of that is the YZ term of P to the 6. So we are able to compute this joint distribution. And likewise, we can compute any other joint distribution we want. Okay. So this somehow gives us a complete description of the trajectory of this Markov chain. Let me give you an analogy at this point. So Markov chains are a very basic model of random dynamical systems, in much the same way that differential equations are models of deterministic dynamical systems. So what does it mean to solve a differential equation? To solve it means you can specify the complete trajectory starting from any given initial condition. Here the trajectory is random, so the equivalent statement is to be able to associate a probability with every possible trajectory given the initial condition. And that's exactly what we are doing here in terms of the transition probability matrix P. Okay, so I hope I've convinced you at this point that specifying this single matrix P tells us everything we want to know about our Markov chain. Okay, so one way to represent a Markov chain is in terms of this transition probability matrix. Another way, which is also something we'll use quite widely, is in terms of its transition probability matrix. This is a pictorial representation. It's often quite easy to visualize things this way. So in a state diagram, we represent each state by a circle, and then we draw arrows between circles for all possible transitions, one-step transitions of this Markov chain. And we label these arrows with the transition probabilities. So again, an example will make this concrete. So let's draw a state diagram for the Drunkard's walk example we saw earlier. So the state space consists of the home or state 0, the lampposts 1 through n, and the pub. And then we can draw arrows between these states. And so there'll be an arrow from state n to the pub, and that will be labeled with half to say the probability of that transition is half. And from n to n minus 1, there'll be an arrow also labeled with half. Similarly, there'll be an arrow from 1 to 2 with label half, 1 to home with label half. What happens from the pub? Okay, so that depends on how we describe it. Let's say once the drunkard gets to the pub, he stays there forever. In that case, there's an arrow from the pub to itself, labeled 1, the probability of staying in the pub. Similarly, there's an arrow from home to itself, labeled 1, meaning that once he gets home, he stays there forever. And that is the state diagram for the drunkard's walk. Okay, next. Let's go back to our analogy with differential equations. So when you were studying these, one thing you wanted to do is solve the equations to work out trajectories. But that wasn't the only thing you were interested in. You also wanted to understand the long-term behavior of these differential equations. And what are some of the things that can happen in the long term? You can have fixed points and then a trajectory started anywhere ends up at one of these fixed points. You can have more complicated limiting sets, again, such that trajectories started anywhere end up in one of these invariant sets. And so to understand the long-term behavior of the differential equation, we wanted to characterize all the invariant sets. And there's something similar with Markov chains. Again, we want to see if there are some analogs of invariant sets, which will turn out to be invariant distributions. And then we can ask, does the Markov chain started in any initial condition end up in one of these invariant distributions? Okay, so let's start by looking at one step, what happens to distributions over one time step. So let's denote by mu sub t the probability distribution of the random variable xt, the state of the Markov chain at time t. So this is, xt is a random variable, so it has some distribution. And this is a probability distribution on the state space, the set of all possible values that xt can take. So we denote by so think of mu t as a row vector, and the xth element of this row vector is the probability that xt takes the value x. So the row vector is indexed by the state space. The elements of the row vector are elements of the state space. Okay, if I give you mu t, what happens? What's the probability distribution of xt plus 1? Where's the Markov chain at time t plus 1? Let's calculate this. So the probability that at time t plus 1, it's in state y, is obtained by summing over all possible states in the state space, the probability that it was in x at time t and ended up in y at time t plus 1. The probability that it was in state x at time t is mu x of t. That was the definition of mu t. And then the conditional probability of going from x to y in one time step is pxy. So we are summing over all possible x of mu xt times pxy. And again, this is the matrix multiplication formula for a row vector times the matrix. So this is the yth element of mu times p. And so the yth element of mu t plus 1 is the yth element of mu times p, or more generally, the row vector mu t plus 1 is mu t times p. Okay, so this tells us how the distribution propagates over time. Now, suppose there is some probability distribution pi on the state space. Okay, there's a typo here, such that pi is pi times p. So if we can find a row vector pi, which solves the equation pi equals pi times the one-step transition probability matrix P, then what that says is that if the Markov chain at time t has distribution pi, then so does the Markov chain at time t plus 1, because pi, that's pi times p, which is also pi. And so does the Markov chain at time t plus 2 by repeating the same argument, and so on. So the Markov chain, so the distribution stays constant over time. So that by going back to the analogy with differential equations, that's what an invariant set is. If you are in that set at some time t, you are in that set at all future times. And in the same way here, if you're in the distribution pi at time t, you are in the distribution pi at all future times. Okay, so the question is there such a distribution? Okay, we call such a distribution invariant if it exists, and the question is, Is there such a distribution for every Markov chain? And we can then also ask, is it unique? So these are two natural questions to ask. The answer to the first question turns out to be no in general. But for the case of most interest to us in this course, most of the Markov chains we look at in this course will have finite state spaces. And in that case, it always has an invariant distribution. So for us, it'll be yes, but in general, it's no. And you should all have seen examples in probability 2 or equivalent courses from the past of Markov chains that don't have invariant distributions. The second question is it unique? To answer this question, we have to discuss some other topics, which we are going to do shortly, and we'll introduce some more concepts before discussing conditions for uniqueness. But I want to end this first lecture by saying, by discussing how to find invariant distributions if they exist. And this is very easy to do. So we saw that if an invariant distribution exists, then it has to solve this equation pi times p is pi. This is the definition of invariant distributions. Well, what's this? This is just a set of, if you rearrange things, it's pi times the identity minus p is 0. That's a set of simultaneous equations, simultaneous linear equations, and that's straightforward how to solve. You've all seen that in first year linear algebra. Okay, so, and that's also why on a finite state space, these always have a solution, but on an infinite state space, things can go wrong. Okay, so all we need to do is solve this set of simultaneous equations and we get a solution. If you solve these, you will find that the matrix I minus P is not full rank. It has rank if your state space is of size n, so if there are n equations in n variables, then it will typically have rank n minus 1. It may even have smaller rank. So there are many solutions to this set of equations. And which one should you pick? You can also see that if pi solves this equation, then so does every multiple of pi. And that gives us a clue as to which multiple we want. Pi is a probability distribution, so the probabilities have to add up to 1. So you get this extra equation, the normalization condition. So you get n plus 1 equations in n variables, and typically n of these are linearly independent, and you can get a unique solution. If the Markov chain has a unique invariant distribution, then you can find it by solving these n plus 1 equations. And if it doesn't have a unique distribution, you can also find all possible solutions by solving the first global balance equations together with the normalization condition. Okay, so that's pretty much what I wanted to cover in the first lecture. So what have we seen so far? So we've seen what a Markov chain is in discrete time. We have seen that it's fully described by the one-step transition probability matrix, and we can also describe it pictorially with a state diagram. We saw how to calculate all joint distributions in terms of the one-step transition probability matrix. And finally, we saw how to solve for invariant distributions by solving the global balance equations, at least when the state space is finite. Okay, so we'll stop here, and in the next lecture, we are going to look some more at the long-term behavior of the Markov chain.